Um, Welcome back to another video with subspaces and vector space, and we're gonna focus on spans. uh, or finding what things span to. And this is still in the week of spans, bases, and a linear combination. So let's get right to it. So this question is gonna ask us, what is the span of the following vectors equal to? So if you recall in the lectures, if we want to find what a span or what a vector spans on, we basically have to see like the dimensions. So if the two examples that I used would be for a plane, or like, yeah, an xy coordinate system. We'll have the 1 0 and the 0 1, and so that would be its bases, or its span. And so it has it has two elements. So anything that's two elements will span in a 2D space. And then the other one, if it was 3, so the 1 0 0, the, what is it, 0 1 0, and then, oh, this is the bases. And then the, what's the other one, 0 0 1, we have 1 2 3, so it spans to the third dimension. And so what we're going to do here now is we're going to, like, given these three vectors, we're going to see if or where do they span on. And so we're going to find the span of these three vectors, and then from there we're going to see if any one of them is a linear combination of the other two, or if we're going to have two. So just by, like, hindsight, just plain, it is possible that we can have one linear dependent vector, two or three linear independent vectors. But we're gonna see how, or which one is which. And so the way we're gonna do it is we can put this in, pretty much put this in augmented form. So what we can do is we can just have, if a times 1 negative 2 3 plus b multiplied by 2 negative 1 3 is equal to 4 to, yeah, that's a terrible 2 to 5. And we're just gonna put this in augmented matrix and then see if it's a linear combination. And so we're gonna just go ahead and get right to it. So 1 negative 2 3, 2 negative 1 3, and then our 4 2 5. Okay, so now we had to pretty much put this in we could put it in row reduced echelon form, or we can, I think, yeah, putting it in row echelon form should also do the trick. So just gonna go ahead and get right to it. So the first one, we can get rid of this 2 here, this 2 right here. And so what we're gonna do is we're gonna multiply, or no, we're gonna add r2 by twice r1. And so we're gonna have 1 2 4, and the bottom one stays the same, 3 5 5. And then we're gonna have 0. Then we'll have 2 times 2 is 4, minus 1 is 3, and then 4 times 2 is 8, minus, not minus, plus 2 is 10. All right, cool. So now what we can do is we can also get rid of this, or one of the 3's, but this 3 right here with the same one. And so now what we're gonna do is take r3 and I subtract it by 3 times r1, and that was going to give us a new matrix. So the first two rows are going to stay the same, 0 3 10. And then we're going to have 0, and then 2 times 3 is 6, which is negative, plus 3, negative 3. 4 times 3 is 12, plus 5 is 7, negative 7. Yeah, negative 7, because it's negative 12 plus 5. And now, well, we can, lucky for us, we can get rid of this negative 3 just by adding row 2 and not having to like multiply or anything. So row 3 plus row 2, that is going to give us let me actually move down a little bit. That is going to give us 1, 2, 4, 0, 3, 10, then 0, then 3 minus 3 is 0, and so 10 minus 7 is 3, and we're pretty much done here, because as you can see here on the what is it, third row? Yeah, third row, this becomes inconsistent. Like, bro, a times 0 plus b times 0 is equal to 0, but it wants to equal to 3, which is not true. So that means this portion is it's linearly independent. And then we basically have 3 pivots as well, because you can use the you can use this this 3 to get rid of this 2, and then we can use this 3 to get rid of the 4 and the 10, and just to put it in row reduced echelon form, we're just gonna get 1 0 0 0 1 0 0 0 1, and we can see that each now we can perfectly see that each vector is independent from each other, and so that means, because we have three entries, that means it spans to R3, or the third dimension, and that's how you find the spanning of the given vectors. If we would have something like if it was something like 1 0 0 0 1 0 and 0 0 0, then this will span to a plane. And then if it was 1 0 0 0 0 0, which zeros all the way, this will span pretty much a line. So this would pretty much be a line, this would be a plane, and then this would be in 3D, so the XYZ coordinate system. I forgot what it's called. Volume? No, maybe. No, volume is 3. I don't know. Anyway, I don't know. Anyways, but yeah, that concludes this video. I think I could probably push one more example. Actually, no, yeah, let's do one more example. All right, so in this final example for subspaces and bases, we are given a subspace S of R2×2, so it's a 2×2 matrix. And considering all 2×2 matrices whose trace is 0, it wants us to find a basis S and its dimension. So this is similar to the second example that we did. The only difference is this is a 2×2 matrix, and we're only focusing on the trace, so not a commutative property. So we're not to like some weird difficulty part. So we're just gonna have a matrix M, A, B, C, D, and we want to have this property where the trace of M is equal to 0. And so those, if you don't remember, back long ago when you guys were younger, the trace is literally just the sum of the main diagonal. So for this to be true, A plus D must equal to 0, so A is equal to negative D. And so now we're going to substitute that back in. So we'll have a matrix will be A, B, C, negative A. Yeah, negative A. And we know this is gonna be in the or in the set of S, because A minus A is it's 0. Come on, guys. and that's we're pretty much done. We just have to find the bases and the dimension. And so we can just go on with what we usually do, and just like factor out the A's, B's, and C's. And so we're just gonna get A 1 0 0 negative 1 plus B, which would be 0 1 0 0, and then plus C 0 0 1 0. And that's it. This is gonna be our bases. So our bases is going to be 1 0 0 negative 1 plus, not plus, the comma, 0 1 0 0, and then 0 1 0 0. And that's it. Our dimensions, well, you just count it off. 1 2 3. So our dimension is going to equal to 3. And that's pretty much it. This concludes, hopefully, this concludes all the examples I have for you guys for subspaces, or not subspaces, spans and bases. So now the next couple videos up until the next lecture will focus on linear combinations and seeing what linear independence and linear dependence look like. We kind of did a little bit of it on some of these examples, but we're gonna have some examples solely focusing on that. So yeah, thank you so much for watching, and I'll see you guys in the next video.